Hello class, and welcome to lecture 33 on Curl and Green's theorem. Our non-math recommendation today is the album Lover by Noah Gunderson. It is also available as an acoustic album. So this album came out in 2019, and then the acoustic version came out in early 2020. Curious trivia fact is that this album Lover came out on the exact same day as Taylor Swift released her album, also named Lover, last year. So they have two kind of coincidental titles. Lover was definitely one of my top 10 albums of 2019, and it's just great. Noah Gunderson has a great voice, so go listen. I wanted to start today's lecture by reviewing vector fields and kind of what we've talked about so far with line integrals and the fundamental theorem of calculus. So let's do that. A vector field is a function assigning vectors to points in R2 or R3. And so we've been drawing these as little, arrays of vectors kind of floating all over a plane, or hypothetically in R3 as well. They're pretty hard to graph in R3. But the key thing is you put a vector at every point. And so in 2 dimensions, it looks like a function from R2 to R2, and in 3 dimensions, it looks like a function from R3 to R3. And today is when we're going to start edging our way into 3 dimensions. So we're going to start talking a little bit more about it, and I want to remind everyone that we can work with both of these. So one of the things we started talking about were, so these are vector fields, right? One of the things we started talking about were gradient fields, which are special vector fields, right? These are nice vector fields which show up as the gradient of a function. So if we have some function f from R2 to R, like for example, f is x squared y, or from R3 to R, like maybe f is x squared plus y squared plus z squared, then we can produce a gradient function. And in the first case, we would have the gradient of f would map from R2 to R2 because there's 2 input vectors, so I can take 2 partial derivatives. And in this second case, the gradient would be a 3-dimensional vector field. And so we get kind of 2 different examples, or we get examples in both dimensions of vector fields. So why do we care about gradient vector fields? The answer is because of the fundamental theorem of calculus that we saw last time. So on one hand, we have that if we have a closed curve, and so this integral with loop means closed integral over a closed curve, C, then the integral of the path integral of gradient of f dot dp, so the flow of the gradient along that path, has to equal 0. So we said last time that this is the same as calling the gradient vector field conservative. This is the definition of conservative, but that's the same as being gradient. And on the right-hand side, we said the fundamental theorem of calculus works for line integrals, so even if C is not closed, you can still compute what C is doing, or what the flow is along C, as long as the vector field is gradient, by just computing what f is doing at the end minus what f is doing at the start. So here's my finish point, and here's my starting point. And that looks exactly the same as kind of your classical fundamental theorem of calculus, f of b minus f of a sort of setup. And in the closed curve, we just have this path starts and stops at the same point, and that's how you should think about these 2 things really being the same statement. So gradient fields are nice because these integrals, these path integrals become easy to compute on gradient fields. And as soon as you know that gradient fields are nice, your goal should be to identify when something is a gradient field. So when do we get a gradient field? We said we can use the Clairaut test that says if f is m comma n, so I'm writing as, two coordinate functions, one for what it's doing, what the x component of f is, and one what the y component of f is, then f is a gradient field if and only if this quantity dn dx minus dm dy is equal to 0. And we call this the scalar curl. And today's lecture is about the curl. So we're going to talk about that scalar curl and what it is. And I'm going to point out that this Clairaut test, this was only in 2 dimensions. So we need to try to extend this to understand what happens and can we identify gradient fields in 3 dimensions as well. In 2 dimensions, we said we've got this vector field f parameterized as m comma n. Then we have this interesting quantity that we said was dn dx minus dm dy. So n was the y component, and it got the x partial derivative applied to it. And m was the x component, it got the y partial derivative applied to it. And we take the difference between the two of them. This is defined to be either the curl of f, and this is sometimes called the scalar curl of f, but we will write it just as curl of f, or as the, let's just give this big definition, or the textbook likes using rot for rotation of f, so clear that's rotation, or the thing I originally wrote it as was nabla cross f, so upside down triangle cross f. And it is that third one that we're going to kind of focus in on and try to explain today. And we're going to use that to define curl in 3 dimensions as well. So the way these formulas make sense is nabla is going to be a vector, because if I'm taking a cross product, it has to be a vector. And so nabla is the vector d dx d dy. And we're defining it that way so that, in fact, the gradient of f, where f is a function, let's say gradient of p, where p is a potential function. So if p is mapping from R to R, we said the gradient, that's px comma py, but that's just d dx of p comma d dy of p. And so you should think this gradient of p is like scalar multiplication by p on the right, even though p is a function, but p is a function that takes values in scalars. So if you think about it that way, this is, you can distribute that scalar multiplication to get d dx d dy times p, and that's why this that's why we wrote the gradient as nabla p when we defined it. And so the same thing sort of makes sense for this formula here. And the way that looks is cross products were defined as determinants. So it was the determinant of a 2x2 matrix for these 2x2 vectors of d dx, d dy, m, n. So you should read this as really nabla, which is that top row. Let's put a little blue box on that. So it's nabla cross F, and F is this bottom row that's being cross-producted together. And the reason this definition works for cross-product is because we know that when we have two-dimensional vectors, the way you do cross-product is by taking, for instance, if you have writing in highlighter, if you've got A, B, and you want to cross it with C, D, then what you do is you take the determinant of a 3x3 matrix and where you pretend like these are the vectors, you turn them into 3x3 vectors where so your z component is 0. And then you just look at what your z component is coming out. So if I did that in 3 dimensions, that would look like I, j, k hat A, B, 0, C, D, 0. And you know what, let's color those zeros blue because I want to show that nothing's happening here. So if I take this cross product, you'll get a vector whose I component has to be 0, whose j component also has to be 0 because of those two zeros, and the k component is AD minus BC. Which is the same sort of cross product here. The AD is dx dn minus dy ddy of m, dm dy, right? And so a cross product of two-dimensional vectors always came down to the z component of the three-dimensional vectors. So this should agree with your kind of definitions for determinants above, and that's how we're going to define the curl also in 3 dimensions. So let's do that. So let's not scroll down too far. Let's keep it all in mind. So in 3 dimensions, the standard is to use F. To write F, well, it has to have 3 components now. So let's call the x1 U, the next one V, and M. I'm doing this to avoid using M, N, and O because O looks like a 0. So, but people use any sorts of combinations of letters here. Then the curl of F, nabla cross F, looks like the determinant of the matrix I, J, K. It's nabla cross F, so it's D, dx, D, dy, D, dz, U, V, M. And so the secret thing that's happening here is that nabla depends on what dimension you're looking at. So nabla here is the vector D, dx, D, dy, D, dz, which is also what it has to be to get gradients in 3 dimensions because it's taking all of those 3 different partial derivatives. And so the determinant of this becomes kind of a big, complicated mess of a formula. So maybe rather than writing it down, I will say that this, you're probably good at computing cross-product formulas. This definition here is the one to memorize for curl. So what I will do is redefine this to either be, so we're defining this to be the curl of f or nabla cross f. But I'm going to point out that because we still have those I, j, and k's, the curl here, this is a vector in R3. And so in 2 dimensions, we have a scalar curl, and in 3 dimensions, we have a vector curl. And let's just make that really clear. In R2, nabla cross f is a scalar curl. In R3, nabla cross f is a vector curl. But as we already saw, you can take these 2-dimensional ones and just look at the z component of what they would have as a 3-dimensional curl, where you set the z component to be 0, and you're going to get the right thing. This is maybe worth spelling out, so let's just notice this. So if you take a 2-dimensional vector field, n comma m, and you turn it into n comma m comma actually 0. Actually 0. Then 2 things happen when you try to compute the vector curl of f. So that's I, j, k, d dx, d dy, d dz of this n m 0. Let's put a slash through 0 to make sure it's 0. And the thing you notice, and I'm taking determinant of this, is that both of these functions, n and m, only are functions of x and y. They have no z's in them because they were 2-dimensional vector fields, or f was a 2-dimensional vector field. That means taking the derivative with respect to z is identically 0. Actually 0. Because when you apply d dz to n or d dz to m, you get the 0 function because they're both constants with respect to z. That means this whole determinant becomes the determinant of ijk, dx, d dy, 0, 0, n, and m. So then that's actually 0, 0 because of those 2 zeros, and the z component becomes nx minus my, which is exactly the scalar curl in 2 dimensions for f. Okay, now I kind of accidentally muted myself in the middle of recording that, so the voiceover is a little weird, and I realized I have a mistake, which is that I swapped my n and m coordinates, so let me fix that right now for you. So I like how I have them here because that's the standard order, m comma n, alphabetically, so I need to update these to be m comma n instead of what I wrote, m comma n. Then over here, this is also m, not n, and this one here should be n, not m, and then everything else makes sense, but that's just relabeling, so, but yeah. So we get the scalar curl, as I said. So a very important question is, what on earth is the curl of f measuring? I said rotation, I said curl, we've written it down, we've computed it as a determinant, but what is it actually doing? And in order to understand this, we're going to look at a kind of basic example in R2. So consider a two-dimensional example. So look, so we've got f, and that's going from R2 to R2. I'll write f as m comma n. Now I'm going to pretend that f is only changing as you change the x values. So so m and n both only depend on x. And so imagine what you have is you've got this vector field in space, and you drop, and you think of the vector field as flowing water. And what you do is you drop a beach ball in the vector field. So you've got this beach ball floating in your vector field. And let's assume first that dn dx is bigger than 0, but because they both depend on x, dm dy is just identically 0, so I don't have to care about that. And remember, my scalar curl looks like dn dx minus dm dy. So in this case, where dn dx is positive, and I'm getting rid of the d dy garbage, the second term, this is positive. So what does positive curl look like? Well, over here, you can imagine that if at this left-hand point of the beach ball, I draw my vector field, and let's say at this point it's going straight up, and it looks like that vector. Then as I move to the right, over to here, this side of the vector of the beach ball in the water, since dn dx is positive, dn was my y component, and so you can see that at this point, it looks like I've got a vector 0 in the x component and maybe like 1 in the y component. And so my m values can't change. So my m value over here for my vector field still has to be 0, but my n values have to be increasing. So this has to be bigger than 1. So let's say maybe it's like 0, 2, or something like this over here. And you end up with a longer vector on that side. Now you should imagine that this is essentially, water is flowing past this ball, moving up, but it's going faster on the right side, so it's going to push the ball more. And so you could essentially say that maybe this much of these two arrows is just trying, because that's the part that's equal to the left arrow, that's just pushing the ball equally. It's kind of balancing the two forces on the left and right side of the ball. But this excess force on the right is going to make the ball spin. And so this ball will, as you drop it in the water, start spinning. Maybe it'll move, but if you hold it fixed at this center point, it's going to spin. And it's going to spin counterclockwise. So I'm going to use CCW and CW for counterclockwise and clockwise. So positive curl, the big takeaway is that, positive curl is the same as counterclockwise spin, or a counterclockwise rotation. And then let's also figure out what negative curl would look like. And so negative curl, again, if we make this assumption that ddm, or dm dy, is 0, then dn dx has to be negative in order to make this true. Then we'll get curl less than 0. So if the curl is less than 0, then when I drop this beach ball, what does the beach ball picture have to look like? I've got this beach ball. I am fixing it around this axis in the middle. You can also imagine that this is like a, like a water wheel or something, spinning. And let's repeat the same story. So let's say the force over here is up. Then as I move to the right, the y force can't change, but the x force has to decrease. So maybe it would become like that. Or in fact, it could be pointing down. It could be negative. It's like in the y direction. Either way, this is going to contribute, like this left force wins this battle and makes this water wheel spin clockwise. So negative curl is the same as clockwise rotation. And so curl is measuring whether you have rotation in your vector field, which is why people like writing rot for the scalar curl. Yeah, and so gradient vector fields in R2 are ones where there is no rotation, no local rotation. If you drop a beach ball in there, it's gonna not rotate. And now I didn't also do this analysis for DDM, but you could kind of do it the same way. Say, what if instead you make dn dx equal to 0, and then you make dm dy positive, or dm dy negative? And recall again that our curl, nabla cross f, looks like nx minus my. So when my is positive, this is going to be giving us curl f, because it's positive but there's a negative on it, it's going to be below 0, so negative curl. And this one's going to give us positive curl. And in the top case, our little beach ball example, instead of moving left to right, imagine you just start at the bottom and you're moving up the beach ball. So here, imagine you've got, some vector to the right like this. Since dm dy is, so it's all concentrated in the m component of the vector field. It's all in the x direction. Then, since dm dy increases, as you go up, you're going to have to get longer, and this is going to contribute to spinning your wheel clockwise, which agrees with the rotation that we got above for negative curl. So both dn dx being negative and dm dy being positive are contributing clockwise rotation. And the argument goes the other way. For this lower one, if you're this long, you have to be shorter up here, which is going to contribute counterclockwise rotation. And that's why this scalar curl measures rotation in the vector field. And we'll get a better sense of eyeballing this as we go forward. But let's talk about Green's theorem. I lied. Let's look at a couple examples of positive curl. So all three of these vector fields have positive curl. You should be able to compute each of their curls. So over on the left example, d dx is 1 minus, and ddn is 1, and dn dx is 1, and dm dy is minus 1, so 1 minus minus 1 is 2. So over here we've got curl f equals 2. In the middle, we have curl f equals 1. And on the right, we have curl f equals 1. So these are all good examples to have in the back of your pocket. And you can see that basically I've taken our favorite counterclockwise rotational vector field. So if anything should have positive curl, the one that we've said is rotation counterclockwise, our like canonical example, should be positive curl. And then I also looked at kind of each of its components on their own, and each of them also is positive curl. And so you should, visualize for yourself that it doesn't really matter where you put your beach ball in any of these examples, you're going to get that it will start spinning. So certainly if you put it at the origin, it's going to be spinning that way over here. But even if you put it kind of out here, you'll notice that the forces on the outer rim are bigger than the forces on the inner rim. So you're going to have a net force on this little disc that makes it spin counterclockwise. And the same is true as you kind of like spread that around radially. In the second example, if you imagine dropping a disc here, there's bigger forces on the left side, which are going to make it spin than there are on the right side, so it's going to spin counterclockwise. If you do it right at this like division boundary, it's pretty obvious that it spins counterclockwise, down on one side, up on the other. And then, as you move kind of like slightly out, it also still looks bigger on the right than on the left, going up. And the same arguments kind of work over here. You can make it spin like that, or this one like this. I'm trying to draw them kind of in varying sizes, varying places, but it should be consistent like this because the curl is just a scalar in all of these. Now, let's look at Green's theorem. So Green's theorem, our first or second, or I guess third reformulation of the fundamental theorem of calculus. And we will justify why that is later, says that if f is a vector field from R2 to R2, and it has continuous partial derivatives, meaning for each of the components, m and n, on a closed region R. And so I'm going to draw a little picture over here. We've got some sort of region R. Let's shade it in. Boom, there's R, shaded in. So it's closed. C is the boundary of R. So recall that we wrote boundary as dr, this partial derivative of R, equals C. And C is oriented counterclockwise. And sometimes that's phrased as inside R is to the left of C. And this inside to the left, outward, right, inside, left orientation we're going to keep using. So even though this might seem like a weird way to phrase it, keep it in mind. So inside is to the left. Then what does that picture have to look like? Here's C going around the boundary. Let's do C in blue. So C. And C is going all the way around. It keeps going in this direction. And you can, I didn't like that. So you can check that as you move along C in this orientation, the inside is to the left, as desired. Then, and here's the big conclusion, the integral around the closed curve C of f dot dp, so the flow of f along C, is exactly the same as the double integral over R of the scalar curl of f dA. And just point out, this is a scalar, so it's assigning to every point inside of R some scalar number that's associated to the x and y coordinates, which is amazing. So take a moment, pause this, record this, and just memorize the Green's theorem because it's so useful. So recall, we said that if f is in 2 dimensions, the curl of f, the scalar curl, being equal to 0 means that f is a gradient field, f is a conservative field, f is a path-independent field, and f is an irrotational field, sometimes people say, and the book occasionally uses, so let's introduce that. Irrotational because it has no rotation. So let's line that up with Green's theorem. So in Green's theorem, we had this, recall we've got some region R, and C is going around the counterclockwise. So it looks something like that. Then we had this double integral over R of the curl. So we've got the scalar curl of f dA. And Green's theorem tells me that's the same as the integral around the closed curve of f dot dp. So the flow along C. Well, if f is irrotational, or a gradient field, so if the gradient of f is 0, or the curl of f is 0, then this left-hand side, that's just 0. So this is an integral of 0. But conservative was the same as saying that this right-hand side was equal to 0. So Green's theorem implies the theorem above. So Green's theorem, if you remember it, will tell you this theorem above, at least in the conservative case. And then if you remember that a conservative field is the same as a gradient field, you can know that it's gradient and path independent and etc. So Green's theorem is kind of focusing in on these path integrals around closed curves, and telling you in particular, when f isn't a gradient field, what is the path integral over a closed curve equal to as a 2-dimensional integral that we can compute, hopefully easier. Or, I should note, sometimes the right-hand side is easier than the left-hand side. So we're kind of going to see both examples where we use Green's theorem to go left or to go right. As for why this is a fundamental theorem of calculus, well, let's talk a little bit about it. So the thing is, the fundamental theorem of calculus for line integrals, if we compare, we had this C, and maybe here C was going from the start to the stop of the gradient of f dot dp. So now, you know what, let me, excuse me, where, let's say p is a potential function. So we've got p from R2 to R. Then this was the same as p at the end minus p at the start. But you should compare that as this left-hand side is a one-dimensional integral. It's adding up coordinates over this whole one-dimensional object as you move from the start over here to the stop, you kind of have a, an interval's worth of numbers that you're adding up some value at. This left-hand side, this is zero-dimensional. So integrals add up infinitely many things, one at like every little point, but this is just adding up a point here, the start, and the end, as just checking at those 2 points. So the fundamental theorem of calculus is taking something one-dimensional and turning it into something zero-dimensional. Likewise, Green's theorem is taking something, and I'm going to use the same notation I used before, R. So here's R, and here's my curve C. It's taking something, this is a two-dimensional integral. I take the scalar curl of f, dA. This is implicitly two-dimensional because I have to go over this whole interior of R, which is itself a two-dimensional object, and I'm integrating over area, an area form, right? And it tells me it's equal to a one-dimensional integral over C. It turns out to be a closed curve, so we put that loop there, of f dot dp. And this right-hand side is now one-dimensional. And so what I'm telling you is the fundamental theorem of calculus is anything that tells you something that's the same between an integral over one dimension and an integral over one dimension lower. And zero-dimensional integrals just look like addition. They look like sums. So that's why the ordinary fundamental theorem of calculus and the one for line integrals look the way they do. But in higher dimensions, it's going to look like I'm going from something two-dimensional and I'm producing something one-dimensional. And sometimes it'll be that this will be the hard thing that we're given, and we'll use Green's theorem to go back to maybe this is easier, and we'll compute it over there. And other times, we'll start with some hard integral over here, and then we turn it, using Green's theorem, into an easier integral around the boundary on the right. And so the question between whether a one-dimensional or a two-dimensional integral is harder than the other is actually a case-by-case basis, whether we think the integrand is harder or whether we can use polar coordinates or something like that. And we are going to see tons of examples right now. Okay, for our first question, I'm going to let C be a rectangular path whose corners are -2, 0, -2 pi, 3, pi, and 3, 0. And so it's going around this rectangle counterclockwise. So let's just make that clear. I'm always going to use counterclockwise. As my default orientation. And what I want to do is compute this integral. The integral over the closed curve C of e to the minus x squared over 2 plus y dx plus 2x dy. So what I would first do to make sense of this is unpack this way of representing the integral into a flow along a curve integral, into a line integral. So what I do is undo the dot product. So I want this to look like dx dy. So this is really the integral over C of a vector field e to the minus x squared over 2 plus y, comma, 2x dot dx dy. And this is dp, and this we're going to let be f. And the first thing you should do is not try to parameterize this path and compute what the integral is, although you can try doing that. But already it looks like this e to the minus x squared over 2 is going to be just impossible. Like, that's an impossible thing to integrate normally. So something's going to have to give in order for us to be able to do that integral in one dimension. And so you might say, hey, this is a closed region, so maybe instead I can swap to this interior of this rectangle. So let's name that R for rectangle, and maybe compute this as the double integral over R of the scalar curl of f dA. And integrals over rectangles are already kind of nice, so I'm hoping that I'll be able to compute that integral easier than this starting integral. So the one thing we really have to do is check what the scalar curl is. Because this is in 2 dimensions, I can use my nx. So this is going to be n, and this is going to be m. This is nx minus my formula, so I don't have to do a big cross product, just a 2-dimensional one. And what I get for nx, for the curl of f, is 2 minus what I get for my. Oh, well, with respect to y, that e to the x squared over 2 is a minus x squared over 2 is a constant, so I just get 1 from the y, which adds up to be 1. So this whole complicated integral that they wanted, let's just call it I. By Green's theorem, I get to conclude that I is equal to the double integral over this rectangle of 1 dA. Now, I can only apply Green's theorem if these coordinates m and n both have continuous derivatives on the region R. But that is true for this these functions, right? So e to the minus x squared over 2 plus y and 2x have arbitrarily many partial derivatives, both with respect to x and y. So they're infinitely differentiable, which most of the time we're going to be in that case, and Green's theorem you can apply very easily. So the scalar curl was much easier, was a much easier integrand to deal with than this vector field that we started with. So our conclusion should be that this is, when I take the integral of 1 dA, I just get the area of R. And so I go back up to my original problem, and my coordinates here, so this is minus 2, 0. This is the point 3, comma 0. This is, this one up here is minus 2 pi, and this is 3, comma pi. And so the height of this rectangle is pi, and the width is 5. So this is 5 pi. And I'm just done. And that is the power of Green's theorem. And it should feel like I'm using the fundamental theorem of calculus. I started with some sort of integral that was really, really hard, but I just converted it into something that was much easier to compute. And this is a good example of how going from 1 dimension up to 2 dimensions actually can be a lot easier than the 1-dimensional thing you started with. Example 2. Let f be the vector field sine of x minus y, comma cosine of y minus e to the minus 2x. Let C be a closed curve in the plane. Is the flow along C clockwise, counterclockwise, or 0? We should rephrase this part of the question, because flow along C, well, if we let C be oriented counterclockwise, then the flow along C is computed as the integral of f dot dp along C, and I'm using a circle because C is closed. And it's clockwise if this is positive. Or sorry, it's counterclockwise. So positive integral means counterclockwise flow. If c is oriented counterclockwise, it's negative. If means clockwise flow, and 0 means 0 flow. So because of so this rephrases the problem into just computing whether this integral is positive, negative, or 0. And the thing I know about that integral is f, the components of f are have continuous derivatives of arbitrary degrees. So they have derivatives of all degrees. So I can use Green's theorem. So let R be the interior of C. Then the integral over C of f dot dp is equal, by Green's theorem, to the integral over R of the scalar curl. And so the one thing we need to compute is the scalar curl of f, and that's, I go up here, I take n, and I take compute nx, that's the cosine y part vanishes, and I get minus 2 times minus e to the minus 2x, so that's plus 2 e to the minus 2x. And then I'm going to subtract what I get from m. So maybe I should, in fact, write subtract like that. My, let's be clear, this here is nx, and I'm computing my. I look up there and say, oh, well, sine x is a constant, so I just have minus 1. And so the scalar curl here of f is 1 plus 2 e to the minus 2x. So the thing I'm going to notice here is we've seen a lot of things where the scalar curl was constant, and in this problem it varies depending on what x is. So that because as x varies, you get different curls. What this should be telling you is that when you drop that basketball or beach ball or whatever into this vector field, at different places it's going to be spinning in different ways. Now, e to stuff can only ever be positive numbers, so you're never going to get a negative number out of this. So your scalar curl, actually, this scalar curl is always positive, because it's 1 plus 2 times something positive. And so you look at this integral and you say, well, it doesn't really matter what R is, what region it is, because the area of R is going to be positive, and I'm adding up this positive function over it. So this double integral of something positive, not 0, but actually positive because of that plus 1 for R dA, has to be bigger than, strictly bigger than 0. So my conclusion is that we are in this positive, therefore counterclockwise answer by kind of lining up all these dots. For the third problem, suppose we have a gradient field in R2 whose scalar curl is approximately 5, or at least it's approximately 5 near C1 and C2. And I have these two different paths, this blue path C1 in the plane and the red path C2. They both start and stop at the same point. I know that if I take the flow along the path C1, what I get is 85. And what I want to do is estimate what the flow is along C2. Now, F is not path independent. Because the gradient is 5, not 0. So it's not going to be the answer that, it's not going to be true that the integral over C2 equals 85 as well. If it were the case, and it were the case for any other path, then F would be path independent, and its gradient, or sorry, its scalar curl would have to be 0. We know it's 5, though, so we have to figure something else out. So what we do is consider the path, do C1, and then do C2 backwards. And so I'm going to write that as C1 minus C2. So that's C1 forwards, C2 backwards. So just like with ordinary integrals, like we can add path integrals, and you see this in the textbook. You can add path integrals as long as you can concatenate where they start and stop. So you can do C1 and then do C2 going backwards, but you can't do C1 going forwards and then C2 going forwards. Those are just kind of two different integrals. But if you do C1 going forwards and then C2 going backwards, you've created a big loop. So C1 minus C2 is a closed curve, and it's the boundary of this green region. So let's just call that R. Now is where I check myself and I realize C1 minus C2, it's a closed curve, and it traverses the boundary of R, but it's doing it clockwise, not counterclockwise. So in order to use Green's theorem, I'm going to have to add a negative sign. So I could either take C2 minus C1, the one going counterclockwise around, and use the integral of R, or I could just add a negative sign on the integral of R. This is the same as to how if you do an integral going left to right versus right to left, you add a negative sign. So what Green's theorem tells me, and I'm going to use it for C1 minus C2, tells me that the integral over the closed curve C1 minus C2 of f dot dp, that's the same as, well, minus what you would get as the integral, and that's the extra minus sign. So let's just highlight it. That's fixing the orientation. Of the integral over this region R of the scalar curl dA. And now the scalar curl of f is basically 5, so I can look at that region, and I didn't give any scale, but I'm going to assume this is a 1-to-1 scale of my axes. So this is 1, 2, 3, etc. Then the area of R, I can just add up all of those 1-by-1 squares, and I see that it's 1 plus 5, so it's 6, 7, 8, 9, 10, 11. So this is basically the minus the integral of 5 dA of R, and the area of R is 11, so this is minus 55. Right, and maybe these curves are, C1 and C2 aren't exactly following those grid lines, but this is all an approximation. So I only have an approximation here, and basically my area is essentially 11, or is approximately 11 for this problem. Well, now let's expand the other side of this equal sign. So the integral over C1 minus C2, so we know that's secretly minus 55. I don't like where I wrote this. I'm just going to give myself more space. The right-hand side. I'm now going to expand this left-hand side. And what I'm going to expand it into is, that's an integral over do C1 then C2 backwards. So that's the same as doing the flow over C1 of f dot dp minus the flow over C2 of f dot dp. Right? Doing C2 backwards is going to give you the opposite of whatever the flow is. On C2 going backwards, right? So, or opposite of the flow on C2, I guess is the way I've written this, because I also included the negative sign, right? So the opposite flow from C2, positively oriented, will be C2 at the negative orientation. And now we can just solve for C2. So I guess somewhere in this problem I should have written that here I'm getting an approximately equal. So this is really an approximately equal to 55. So I get to conclude that if I solve for the integral over C2 of f dot dp, it's approximately equal to, so I'd have to move to the right-hand side, move the other one over, to the 55 plus the integral over C1 of f dot dp. And the integral over C1 we said was, let's scroll up and check, 85. Oh. Yeah. So I've got 55 plus 85. So that's 140. And there's my answer. So my flow along this curve is 140. So just to recap, because this will be the last problem for today, because f has 5 curl, what that's telling you is that the flow along C1 being 85 and the flow along C2 are not going to be equal, but they kind of differ by how much additional flow you have to have on this region R. And so if you imagine that R is, tethered right here in the middle, we expect R to be rotating counterclockwise because of this 5, right? And C1 and C2 aren't the same length. This is 1, 2, 3, 4, 5, 6, 7, 8 by 3, 4, 5, 6, 7, 8, 9, 10. So this is, C2 is more than half of R, but we expect R to be rotating that way. So if you walk along C1 and you realize you have 85 flow along C1, then that's kind of making, giving 85 rotation like in that direction. But this is saying, oh, but actually if you flow along C2, you get 145, or what was it, 140 flow in that direction. And when these guys cancel, you can take a difference. You realize that you have a net positive flow of 55 around R, which is the 55 that is making R spin. So maybe this way of interpreting what curl is and these different path integrals kind of helps you realize what's going on.